So as far as the different types of harmonic sources that we would typically be seeing, these would be at customer loads. And you would have single phase power supplies. So there's a lot of these, but they're not really that large, but they would have an additive effect. You have AC motor drives, DC motor drives. Arc furnaces and welders, if you have those at the distribution level, would have a very high harmonic content. And then you would have maybe some special purpose lighting systems like some discharge lighting systems. Another thing that would create harmonics is also transformers, because transformers have magnetic cores that are nonlinear. And if you have single phase transformers, these can actually generate third harmonics. So anything that has a magnetic core is going to saturate, and is also going to have harmonics associated with it. So anyway, this just shows some typical single phase rectifiers. This design at the top, it's an older style design for power supplies. It used to be a long time ago that we would have a transformer convert 120 to 12 volts. There'd be a diode rectifier, and then you'd have a linear regulator for maintaining a DC output. Nowadays, you would have what we call switch mode designs, and the switch mode designs don't have this step down transformer like the older regulators. What you would have is you would just simply have a line impedance, and then you just goes through a direct AC to DC conversion. And then basically what you do is you convert the DC back to, say, like AC again, and then what you can then do is if you need the DC, then you can go ahead and rectify this and convert back to DC. So this is another type of design that you would see more for like laptop power supplies or computer power supplies. What you'll see on these single phase rectifiers would be they don't really draw a lot of current, because usually the loads aren't that high. But then what you would do is you would see a kind of a current draw in the first half of the cycle and a current draw in the second half in the opposite direction. Usually in steady state, this is normally symmetric. And what this would give you is this would give you odd harmonics like third, fifth, seventh, etc. In this particular waveform right here, if you see at the fundamentals at 15.5, that the third harmonic would be kind of significant, 11.8 amps, and the fifth harmonic would be 6.5. So the dominant harmonic in this case would be the third harmonic. We talked a little bit already about rectification for motor drives. And so when you have a motor drive, you convert the AC into DC, then you convert the DC back to AC. And by changing the frequency and the magnitude of the voltage applied to the motor, then you can control the torque and the speed. And so, you know, these are all controlled switches on the motor side, on the inverter side of this. If you look at the line input current, this gives you what we saw before. It gives you this particular sort of characteristic with these particular harmonics. And of course, this is going to be a function of the load. The link DC voltage is constant for the most part. There's a little bit of a ripple on it. And if you would look at this type of device in the field, here's another measurement where what we're doing is we're measuring the input waveform. You can kind of see you got these two spikes on the positive part of the waveform and two negative spikes on the second half. Then these power quality measuring devices, once they capture the waveform, then you can do a Fourier analysis, and this actually shows the corresponding harmonic content. Now, what you'll again see here is when you have a three-phase device and you're doing rectification, you don't get the third harmonics. What you would get is you would get the fifth and the seventh harmonics. So usually the pattern is you get the fifth, you get the seventh, you get the 11th, you get the 13th. Then usually after that, we're not as concerned anymore. So why are we concerned about it? Well, if you have a load that's producing harmonic currents and you connect that up to a transformer, then you're going to get additional heating. What this does is it adds to the RMS current, and so you're going to get more I²R losses. If you get harmonics in the voltage, that results in more core losses. And so this could cause transformers to overheat. So there's usually a derating factor you'd have to supply, or you'd have to come up with, where you can't load your transformer up as much. You'd actually have to kind of back off on how much loading you put on if it had a lot of harmonic content. As I mentioned before, this is going to overheat motors. And so this is why we're careful in industrial situations not to have too much harmonic in the voltage supply. It affects capacitor ratings because capacitors sink harmonics. And then if you have equipment that's sensitive to a zero crossing of the voltage, some older pieces of equipment would actually get kind of a synchronization from the voltage crossing. This can cause certain types of equipment to misoperate. This could confuse like protective relay. If we had a lot of harmonic content, you would get sometimes what we call these resonant overvoltages, and we'll get into that in just a little bit. And this could also interfere with communications. And so if you have harmonics flowing in the line, especially the higher order harmonics, and you have a nearby phone cable, let's say, then this noise can get induced into the phone cable and can actually interfere with communications. So when we're talking about the impact of the system, the other thing we have to worry about is how does the system impedance change with frequency? Before, we didn't have to be concerned about this because we were just working with 60 hertz, but let's suppose that we have this as an equivalent model for the power system. We have a source, we have a system series impedance, then I have like a power factor correction capacitor in here. And then I might also have some load damping as well. So what's going to happen if I have a harmonic source? Well, one thing we can do to make this a little clearer is we can take this Thevenin equivalent for the circuit and we can convert this to a Norton equivalent. This is a current in parallel with impedance. And what you see is you have both of these current sources injecting into an equivalent impedance where you have something that we could maybe have a lot of inductance associated with it. You have resistance and you have capacitance. And whenever you have a parallel combination of inductance and capacitance, then you start to have potential for what we refer to as resonance. All right, so there could actually be a situation when these capacitors and inductors are in parallel that we could actually get an impedance that's pretty high at certain frequencies. And if we're injecting a harmonic at a resonant frequency of the circuit, then overvoltages could occur. So for example, if I were going to plot this impedance, this parallel RLC impedance, I might get a characteristic, sorry about that, I might get a characteristic that looks something like this right here. Need to move something on my zoom settings. So you can see that what it's doing here, it's peaking out around 500 hertz or so. And so anytime I have a harmonic being injected that's at this point in the curve where it kind of spikes, then this means I can get what's called a resonant overvoltage. And this is going to be limited. The amount of this peak is going to be kind of reduced by the amount of resistance in the circuit. But the resonant frequency is going to be about 1/2 pi times the square root of LC in terms of hertz. OpenDSS could actually plot this resonant response. And so I've just got some sample code here, but once you put in your line model, what you can also do is you can also get OpenDSS to work in the harmonic domain. And actually, if you give it the right commands, it'll actually do this harmonic scan for you and then figure out for a given harmonic source and what happens to the voltages in the circuit as a result. So anyway, this is something we always have to be on the watch for. If you have harmonic currents injected by a load that are frequencies where the system impedance is large, then we have the potential for some really high harmonic overvoltages and something's called resonant overvoltages. And this can damage components that are in parallel. So if you have certain loads, these could be damaged by resonant overvoltages. Where this is normally a problem when I put in power factor correction capacitors is essentially near like a fifth harmonic. This is typically where we tend to have issues. So it's around 300 hertz or so. And if we hit this resonant condition, then we have to do something about it. Usually we can detune the circuit to make sure that this isn't going to be an issue. But anytime that capacitor would switch in with a harmonic source that had 300 hertz components, that might actually cause some overvoltages that would maybe blow a fuse, let's say. So anyway, this is some examples here of code. If you wanted to take a look at this earlier, you can do these harmonic scans and stuff like that with OpenDSS. That's another useful aspect of the tool. As far as harmonics propagating in distribution circuits, let's suppose we had a harmonic source inject current. Where does it go? Well, it's kind of like lightning in a way. It basically looks for a path to ground. It looks for the low impedance path to ground. And what would cause a low impedance path to ground? Well, normally we're going to have low impedance paths to ground through capacitors, because the combination of a line reactance in series with a capacitance, usually those are going to interact in such a way that those capacitors are going to make kind of low impedance paths to ground possible. So normally what happens if I have power factor crushing capacitors in a circuit, or power factor crushing capacitors on the customer side of transformers, that if I had a harmonic producing source, a lot of times it's going to be, these currents are going to tend to want to sink where we have capacitors in the circuit. If I don't have the capacitors, that's going to sink toward the source. But if I have capacitors in there, those capacitors are going to be subject to harmonic issues. And so capacitances and harmonic sources don't really mix too well. This is where you have to kind of start being careful. Now, there are standards on how many harmonics we can have in a circuit. And this is actually done through this standard called IEEE 519. 519 is incorporated into the DER standard 1547. So they just basically took the whole 519, rolled it into 1547. This standard's been out for a while, but basically what they talk about in the standard is if you have a harmonic producing load, say at customer side A, you're looking at the impact on customer B. And so this interaction point would be at the point of common coupling. This is a common bus between the two nodes. And so we're looking for how customer A would maybe impact this voltage and cause something bad happening at their neighbors. You've got limits on currents that can be injected at the harmonic levels. And this is a function of the strength of the system. And so where we're injecting the harmonics, we look at what's called the stiffness factor, where this is the ratio of the short circuit current to the current being injected at the load side. And so the higher this value is, the less the system impedance, and the stiffer it is, the more resistant it is to causing harmonic overvoltages due to harmonic currents. And so if we have a really stiff system, then we could really tolerate really high harmonics. So below the 11th harmonic, we could have individual components up to 15% with the total harmonic distortion of 20. But if the system's weak, then these individual components can't be more than 4%. And then the total harmonic distortion is limited to 5%. And so this is a function of the strength of the system. The stronger the system, the more harmonics the system can withstand. As far as the voltages, what we're looking at, and this is also a function of the voltage, but for distribution level, the limit for each harmonic would be 3% with a total harmonic distortion limit of 5%. And so it depends on the voltage we're at, and this is typically the range we're interested in for distribution circuits. And so as a distribution system planner, what you're always on the lookout for is, do you have some industrial customers that could potentially cause these voltages to go up over these particular limits? And if these customers do, cause issues, then they need to do some kind of mitigation strategy. So anyway, these current levels are designed in such a way, these numbers are designed in such a way that as long as these industrial customers stay below this point, then you're going to be okay. However, what happens if you have multiple industrial customers that are they're injecting? Well, then that effect's going to be additive. And then if you get the harmonic voltage up above a certain level, then motors are going to start overheating and transformers are going to start overheating and other things are going to start to happen, right? And so this is something you may have to address on certain industrial circuits with a lot of harmonic producing loads. So anyway, this is just a kind of a final example that kind of shows some of the number crunching you may need to do. And I've got this little system here to the left with the power factor correction capacitor 2400 kVAR, and it's got a resistive load of 2 megawatts. And so we're going to use this to get an equivalent C, R, and L. And I've got the harmonic source here, which is the same as a harmonic source we looked at before. So what we're looking at is doing different calculations. We want to get the short circuit current at the point of common coupling. We want to get the stiffness ratio, so we know what current levels that we need to adhere to. We want to check to see if the currents that are injected at harmonic levels comply with 519. We want to see what the capacitor in the circuit, what the first, fifth, and seventh voltage magnitudes will be. From that, we can get the total harmonic distortion and then see if we violate the IEEE 519 limits. So what we're doing in this particular case now is we going to do these calculations and we're going to have some of these values right here, which are initially going to be in per unit. I'm going to go ahead and convert these over to ohms, because the thing that's a little trickier in this case is we're going to have to get equivalent resistances, inductor values, and capacitor values, so we can do the resonant calculation. All right, so get my pen out. Okay, so for a 12.47 kV system, we've got 15 MVA source. This gives us the base value. If I've got this impedance in per unit, what I can do is I can multiply by the base value, and this gives me this value in ohms. The short circuit current I would have at this bus would be the line to neutral voltage divided by the impedance, and so the short circuit current is 6,945 amps. So if I have a load injecting 106, the stiffness factor is this short circuit current divided by 106, which is 65.5. So whenever going into the tables to get the limits, I'm going to look at the values that are corresponding to 65.5, which fall into this range here. So what this does, this is going to give me the limitations on the individual harmonics and the total harmonic distortion. Okay, then what I can do is I can see where we are as far as THD on the currents. If I got 41 amps at the fifth harmonic and 14 amps in the seventh, I normalize by 106, which is the fundamental, multiplied by 100%. And I got the 38, about 39% for the fifth harmonic and 13% for the seventh. If I calculate the THD, then you can see I'm at 40.87. And so not only do I have my individual harmonics above the limit, that this THD level is way above where I need it to be. Now, if you wanted to see what the impact at different frequencies is on the voltage, then what I could do is I can calculate an equivalent resistance and reactance. The way I do this, if I take V squared over P, this is going to give me equivalent resistance. If I take V squared over Q, this is going to give me equivalent inductive resistance, or reactance, I should say. And so what I have here at 60 hertz, what I have here at 60 hertz of the fundamental, is this equivalent circuit. Okay, I can convert this to a Norton equivalent. Basically, this is going to be the short circuit current. I've got my load, I've got my equivalent load resistance, I've got my equivalent capacitor reactance, I've got my system series inductance. But this is the equivalent system right here at 60 hertz. Now, the problem we run into is I got to look at this response not only at 60 hertz, but I got to look at this response at the 5th and 7th harmonic. I have to look at this at other frequencies at 300 hertz and 420. So in order to do that, I got to take into account that the reactance is going to change by omega times L. The capacitance is going to change by 1 over omega C. So then I can calculate a equivalent inductance for the source. I can calculate an equivalent capacitance for the capacitor bank. So I get a source inductance of 2.75 millihenries, an equivalent capacitor value of 40.9 microfarads. So as far as individual components now, these are going to be the inductance, the capacitance, and the resistance. And now I can calculate the equivalent impedance at different frequencies. And so if I'm doing this at the fundamental, what I do to get the voltage at the point of common coupling, I calculate the parallel impedance and I multiply this by the net injected current, the source current minus the load current. And so what I get in this particular case is I get this for the equivalent impedance at 60 hertz. If I multiply this by the equivalent injected current, I see I got 7,297 volts, right? So that's what I would have at the fundamental, which we're okay with. For the 5th harmonic, what I need to do is evaluate the shunt impedance and the capacitor impedance at the 5th harmonic. And so these values for the reactive impedance will be higher, the capacitive impedance will be lower. I do the same equivalent calculation for the impedance at 300 hertz. And what I get in this case, if I inject in the current associated with the load, and I got to put a minus here because I need this injected, this is going to give me a magnitude of 352 volts. And so I do have a pretty significant voltage at that bus at the 5th harmonic. And then if I look at this at the 7th harmonic, at 420 hertz, I do the similar set of calculations of the 7th harmonic. You see the equivalent impedances change at the 7th harmonic. I come up with a new equivalent impedance. And then when I calculate the voltage at the 7th harmonic at the point of common coupling, this is going to be 431.8. So what's interesting is even though the current level was lower, the voltage level is higher because what's going on is I'm hitting a resonant point. The impedance, the net impedance is actually going up in this case. All right, so this is the thing you have to watch out for is this value becoming large? Because even if you have a smaller harmonic current, you can still have a lot of harmonic voltage if the impedance goes up. And so what we're kind of seeing is we're seeing this sort of effect right here, where this is actually closer in frequency to the 7th than it is the 5th harmonic. So anyway, once you have these numbers, you can get the THD. We see the THD is too high. The allowed distortion level is just 5%. So there's be something we would need to do about this. We're exceeding the total harmonic distortion. We're exceeding the individual limits. And so this is kind of clearly a non-compliant type of a load case for this particular sort of situation. And what we would need to look at is some type of solution, say like filtering, which is kind of beyond what we're going to have time to cover here today. But if you were going to work with power electronic loads, and you would maybe put some type of filter out there to keep those harmonics from going into the power system. So anyway, here's some references on different standards related to quality. The harmonic standard, there's a monitoring power quality standard. There's some standards around impact on equipment. There's a color book series which talks about how to do power system analysis for commercial facilities. IEEE standard 399. So there's a lot of resources around this. And then in Short's book, there's actually quite a bit of stuff in there in power quality because he was at Electric Power Research Institute when they were doing a lot of work on power quality in the 80s and 90s. And so a lot of those results are written up in here. And as I mentioned before, if you wanted kind of like a handbook that shows all the different types of waveforms you could see with the power quality analysis meter, then the Dranitz books are really good for that. Because again, it's like a little picture book that, shows the waveform and say, well, this waveform is due to this. And then they sometimes even have some mitigation strategies in there for how you could fix something like that. And so anyway, this is the end of the power quality material. And what we'll be looking at in the next lecture is we're going to go back to looking at reliability analysis, but we're actually going to look at how we can fix problems through using feeder automation. If we automate switches on the feeder, how can that actually help us with our safety and safety indices?